Webinar. I'm Ann Thayer, contributing editor to the C&EN Media Group, and I'll be moderating today's event. This webinar is entitled 30 Formulations in 30 Hours, Deploying an Unchained Labs Ecosystem to Automate Formulation Screening for IgM Monoclonal Antibody Drug Product Development, and is being sponsored by Unchained Labs. C&EN works with sponsors to identify topics of interest and value to C&EN's audience and consistent with C&EN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. Just a few technical items before we begin. During the webinar, you can adjust the size of the slides on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget or type your query into the Q&A box. If you're disconnected during the webcast, please log in again according to the instructions you received earlier. You're also encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I'll be posing as many as time permits. Please note that C&EN does not endorse any company, products, or services that may be mentioned in the webinars, and that each webinar will be archived at C&EN Online after the webcast. The presentation today is being sponsored by Unchained Labs. The company is all about helping biologics and gene therapy researchers break free from tools that just don't cut it, unleashing problem-tackling solutions that make a huge difference in the real science they do every day. That's the company's mantra, its promise, and they own it. During the presentation, we'll hear from three speakers: Christopher Mensch, Director of Drug Product Development and Research at IgM Biosciences; Samir Sakdeva, Ph.D., Senior Scientist of Drug Product Development at IgM Biosciences; and Kevin Lance, Ph.D., Director of Marketing at Unchained Labs. I'll now hand things over to Kevin.
Welcome to 30 Formulations in 30 Hours, deploying an Unchained Labs ecosystem to automate formulation screening for IgM antibody drug product development. I'm Kevin Lance, Director of Marketing, and I'll be taking you through the Unchained Labs products that we'll see in the webinar today. Many of the original tools used in labs were made for small molecules, not for biologics, so they are usually not ideal. Like using a hammer to hammer a screw, the more advanced therapies get, the more they could benefit from using the right tool for the job. For biologics, screening for only the best antibody or formulation option is a key part of lead identification, antibody engineering, and today's topic, formulation. Today, IgM will cover how they screen 30 formulations in 30 hours using their workflow of Unchained Labs instruments. So first, they'll use Unagi to formulate their IgM antibody into different formulation buffers, and also use Unagi to concentrate IgM to the level it needs to get to. They'll use Honeybun to look at viscosity, and Stunner to quantify for antibody concentration, look at size and polydispersity through DLS, and even look at formulation screening with KD and B22. Let's begin by taking a deeper dive into Unagi. Unagi is my favorite buffer exchange solution. And when it comes to buffer exchange, manual methods just don't cut it. Dialysis is slow, your sample gets diluted, and it's really not quantitative because you don't know what's going on inside that little dialysis bag. Centrifugation is much faster, but as proteins and solutions concentrate, membranes can clog and things can get aggregated. And tangential flow filtration, or TFF, is complicated setups and usually only makes sense if you're dealing with lots of large sample volume. That's where Unagi comes in. It's capable of performing up to 8 exchanges on sample volumes from 500 microliters up to 48 milliliters of each sample, and it does so in less than 15 minutes of hands-on time. Buffer exchange on Unagi happens in UNAs. Each UNA can hold between 1/2 and 8 milliliters of sample volume, and at the bottom of each one there's either a regenerated cellulose or polyether sulfone membrane with a variety of different molecular weight cutoffs. You can see in the right how the holder holds each UNA, and that will be shaken while pressure is applied to the top of the UNA so that buffer can come out through the bottom through the molecular weight cutoff membrane. What Unagi is doing with each sample is automated pressure-based ultrafiltration dye filtration. It begins after you've loaded the samples, and Unagi will measure the volume inside of each una. When it starts to run, it will apply positive pressure while mixing a sample, while shaking a sample, and so that buffer will come out through the bottom of those unas through the molecular weight cutoff filter. After a cycle, Unagi will again measure the volume remaining and refill new buffer if buffer exchange is your goal, and then repeat that cycle until we've achieved a desired percentage of buffer exchange, 95%, 99%, whatever the user wants to set. At that point, the user can even then concentrate the samples to achieve a desired final concentration or volume. This kind of buffer exchange and concentration setup is a more gentle and efficient exchange than dead-end ultrafiltration, because with that orbital mixing step, you're not getting crowding at the membrane as small molecules and water is pushed through. Instead, things are well mixed and you don't have to worry so much about aggregation. All of that's programmable and it's designed to prevent clogging and make exchange even faster. Inside of Unagi, we have a rack of buffers. We have the buffer exchange chamber shown at the bottom of the sample. That's where that pressure is applied during mixing cycle. The UNA sample rack we've already seen. And then number 4 is the pipette channel, which is responsible for automatically adding buffer or sample to each UNA. Hidden up inside behind number 5 is our ultrasonic volume sensor. And of course, in any kind of system where we're going to be moving around buffer with pipettes, we have to have our tip racks. When you run cycles on Unagi, you get protein recovery above 95–96%. So here we're looking at results using human IgG with Unagi's presets for that molecule. And for buffer exchange, we're getting right on the concentration that we want. For buffer exchange followed by a concentration step, we're seeing an increase from 9.9 to 79.3 milligram per milliliter without losing any of our recovery. And reducing sample volume, we've taken 48 milliliters of a sample and increased the volume, or increased the concentration from 0.25 milligram per milliliter all the way up to 1.4, again without sacrificing anything for recovery. So after samples have been buffer exchanged or concentrated on Unagi, next it makes sense to read their viscosity on Honeybun. Usually the problem with viscosity is that getting data is so slow, no one is getting as much viscosity data as they need. Old school instruments use too much volume and only run one sample at a time, and even modern tech that uses lower sample volumes has really complicated workflows that require hours of hands-on time and lots of upkeep. So Honeybun is intended to solve all those problems. Honeybun can take 10 samples at a time and in just a few minutes get viscosity data. And it does this using only 35 microliters for each sample. Samples up to 10 centipoise will run in less than 1 minute, and Honeybun can run a full range of viscosities from 0.5 to 150 centipoise. To prep your sample also only takes a few moments, since all you have to do is pipette your sample into the consumable and work through some of the quickest software steps you've ever seen. How does Honeybun do this? It all starts with its consumable, the bun. Each bun can run from 1 to 10 samples, and any channels that aren't used can be saved for later. To prep for a run, simply add in 35 microliters of a sample into an input well, and that's it. Gone are the days of filling syringes or cleaning expensive chips that are prone to clogging because these buns are disposable. The bun's secret ingredient is the microfluidic channel connecting the input well and the output well. That microfluidics channel has 2 sections, the resistance channel marked by an R and the measurement channel marked by an M. Before we see sample running through those resistance and measurement channels, first let's load a sample onto the Honeybun, which all it takes is a simple push. The loading mechanism works just like loading a memory card into a computer. And then inside of Honeybun, here's exactly what a run looks like. It'll apply pressure, just air or nitrogen, into the sample to push the sample through that resistance channel first. Here's actually in real time how fast samples move through each channel, and that's going to be related to their viscosity. We're looking at water, a 2 centipoise standard and a 10 centipoise standard at positions 1, 2, and 3, and that's repeated twice more on this one. You can see in the overlays how the software is tracking the leading edge of the sample in that measurement channel, so it can later calculate viscosity. If we take video data like that and break it down just a little bit, you can see the same 10 data points alongside the shear rate data behind them. Every experiment includes a sweep of shear rates in each channel, so you can compare how each and every sample is flowing, whether it's Newtonian or not. The viscosity of Newtonian samples will be flat across different shear rates, while non-Newtonian shear thinning or thickening samples will show dramatic change at different shear rates. So that's Honeybun for viscosity. Next, let's take a look at Stunner for protein quantification, size and polydispersity, and KDB22. When it comes to protein quantification, it's a classic graphic, but it's all about accuracy and precision and getting your arrows spot on to the center of that bullseye when you're quantifying exactly what you have. And in the case of Stunner, it's going to give you accuracy within 2% of true concentration value and precision with a percent CV of within 1%. So Stunner is also the quant and sizing mashup. So beyond those amazing concentration results, you're also going to get answers on the size and the polydispersity, or how homogeneous or heterogeneous your size is. And all of that's going to happen on 2 microliters of sample in less than 1 minute per sample without any labels, reagents, or standards. So how this works is we take the Stunner plate, which is a 96 well plate where each well has been replaced by a microfluidics circuit. Inside of each circuit, we add the sample, and inside of Stunner, it's going to do a read on UV vis, use that to calculate concentration, and do a dynamic light scattering or DLS read. That's going to give us the size of the protein molecules in our sample. Here we can see exactly what sample loading looks like with the help of some fluorescein and a black light. In 2 wells, we've already added 2 microliters of fluorescein sample. And as you can see, to load another sample, you simply add in 2 microliters into that input well, and the sample wicks into the plate. Here's what it looks like before and after a read happens. You can see the fluorescein in the microfluidic reservoirs on the left and on the right, where the left is before the sample is read, and on the right is after the samples are pulled into the microcuvettes. You might even notice that one cuvette is brighter than the other. That's because one of them has a longer path length than the other, which means there's slightly more volume of the sample on that one. It's more visible. That combination of 2 different path lengths is part of what gets Stunner its phenomenal dynamic range for proteins. When we're starting to read IgG samples on Stunner, what we get is data that looks like this. So on the left, we have absorbance values across a range of wavelengths, and we see that for octuplicate samples, if we start with a very high concentration in green and then dilute it down, that absorbance will decrease as your sample gets diluted. If we go ahead and quantify that with the absorbance at 280 nanometers, shown on the right, then we can see how that protein concentration gets diluted. That absorbance is incredibly linear with an R squared of 0.9999, which is what you want to see. And for both of these graphs, these samples are measured in octuplicate and overlaid. So even though it's an N of 8, we're actually only seeing a single data point, which speaks to the precision and reproducibility of Stunner. If we then take those 8280 values and use protein's extinction coefficient to quantify the amount of IgG that we have, we can match up the known concentration versus the measured concentration on Stunner and see a slope very, very close to 1 and that amazing R squared value again. And on the table on the right, you can compare the known and measured concentrations and see how our accuracy is within 2% and our percent CV, shown in the last column, is within 1%. Beyond concentration, Stunner also offers DLS, so that when you read a sample on Stunner, you're getting the concentration, of course, but also the size. So in the blue, we have an antibody that's nice and happy, it's homogeneous, we don't have aggregation going on, so we know that we can trust that that concentration value is representative of all of the monomeric IgG that we have in our sample. On the right, however, we do have some aggregation going on. So in this case, we should know that that 1.1 milligram per milliliter of antibody has got some problems and that this sample is already aggregated, and we can choose to not go forward with it, or we can choose to clean it up depending on what we want to use it for. And the other interesting thing you can do with DLS data like this on proteins is take a look at B22 and KD to understand protein-protein interactions in your formulation buffer with your molecule. So in this case, we take a range of concentrations, usually somewhere in the range of between 1 and 10 to 20 milligram per milliliter. We run all of those samples, and on the y-axis, we're tracking either the Kc over R90 value, which is going to be a measure of static light scattering, or we're measuring the diffusion coefficient, which is going to come from a DLS read, more related to size. If across a concentration range, there's an upward trend shown by the green arrow, then we know that Kd and B22, which are the second virial coefficient and the diffusion interaction parameter, those values are positive. We have weak repulsion in our sample, which is what we want. That means it's not going to be susceptible to aggregation, and we're happy with that combination of our molecule and formulation buffer. However, if those values trend down, then we know that our Kd and B22 values are negative, and that indicates weak attraction between our molecules in this formulation buffer. So this is a fast way of just using light scattering and a couple different concentrations of protein to understand if your protein formulation combination is at risk of aggregation. And that's the lineup that IGM will be using to screen through 30 formulations in 30 hours. And this is what Unchained Lab strives to do. We always want to provide the right tool for the right job. And now the IGM team will discuss how they use these instruments in their work.
Thank you, Kevin, for the introduction. We would like to thank you, Dell, the Unchained team, and those at C&EN for this opportunity today. My name is Christopher Mensch, Director of Drug Product Development and Research at IGM Biosciences, and I am joined today by a member of my team, Senior Scientist Samir Sachdeva. Today, we will be telling you the story of 30 formulations in 30 hours, deploying an Unchained Labs ecosystem to automate formulation screening for IGM mAb drug product development. Today, we will present what drug product development entails, a description of a very common activity that encompasses our problem statement, the strategy we employed, our results, and look forward, followed by a Q&A. In drug product development, we are responsible for developing a stable drug product from production to the patient. You see here common pillars of focus, beginning with formulation on the left, proceeding to the demonstration of stability, the process of defining dose preparation, and ultimately proper delivery. Here I describe the phases of drug product development and research. At the top of your screen, you can see those phases divided into 3 different sections, what I refer to as pre-pivotal or preclinical, pivotal or clinical, and commercialization. The activities underneath each of those sections are generalizations for the stages of development, beginning with lead ID and candidate selection, followed by lead optimization or IND readiness activities, achieving IND approval, first in human, a phase 1 trial, followed by then a phase 2 trial, a phase 3 trial, BLA approval, commercial launch, and then lifecycle management activities. Here, I color code those activities into red, yellow, and green, and further define common decisions that are made, broken down by each of those phases. Discovery and developability under the pre-pivotal phase. Then, in the pivotal phase, or clinical, we design and define. And then finally, in the commercial phase, we are seeking to optimize and transfer, and always seeking continuous improvement. With respect to the types of activities in each of these phases, you'll find the preclinical phase very focused on research activity with a clear transition into the development space in yellow. In the clinical phase, the development activity increases as programs move from early phase clinical trials to later stage or later phase clinical trials. As, at the same time, production activity increases all the way through commercialization and lifecycle management. I will note as well that development activity in yellow does continue following successful BLA approval with continuous improvement development activity. So we are on target. Today, the example you'll hear about is a common formulation or reformulation optimization activity that we engage in as the clinical development timeline advances. Here we have our problem statement, which begins with a common development activity, as previously stated, that of reformulation. We have a program in the clinical phase of development which requires reformulation to achieve the target product profile shelf life. And we need to determine a stable dosage form to enable pivotal clinical stage development. And our goal is to recommend lead formulation compositions within 3 months using existing and available material supply and FTEs. However, in the process, as is very common, aggregation was observed upon performing the reformulation buffer exchange process. And as is also common for development teams, we were constrained. We were fighting time constraints, meaning we had days to resolve and resume reformulation activities. And we needed to make a recommendation within 3 months. Further, we were operating with material constraints. Drug substance availability was limited. And further, that material was earmarked for stability activities, not for screening or troubleshooting. And as is commonly experienced, we were still carrying our traditional analytical limitations on both time and material requirements in addition to these added constraints. Here we are illustrating the workflow we created utilizing Unchained Labs technology in concert with existing technologies to perform a very routine formulation screening workflow. However, the automated nature of the workflow enables significantly increased productivity during drug product development, to the extent that we are able to screen and identify 30 formulations in 30 hours. For example, from left to right, we begin the process with our preparation, whether manual or in an automated format, entering this workflow. Second, we move toward another common activity of buffer exchanging and concentrating. In this case, utilizing the Unchained Unagi, where in 2 hours, we are able to buffer exchange and concentrate 8 samples. Following the buffer exchange and concentration process, we then assess viscosity using Unchained Honeybun, where in about 2 minutes, you can measure 10 samples using the device shown here in the middle of your screen and the consumable shown in the bottom, known as the bun. The next step in our workflow, on the right-hand portion of the screen, you'll find use of the Unchained Stunner, where we get a lot of information from this technology. Protein concentration, turbidity, particle diameter, polydispersity, Kd, or the diffusion interaction parameter, B22, known as the second virial coefficient, as well as custom calculations, can all be an analytical output of this microfluidic, very low volume sparing analysis. And in 1 hour, we are able to assess 96 samples in a single plate. Finally, outputting to both benchling and jump.
This slide describes our screening design in simple terms and in an iterative fashion. Our goal was to identify formulations that might be suitable for either liquid or lyophilized dosage form. From the top, we began liquid screening and screened formulations at different pH range with different salts, low and high, and with addition of sugar and surfactant. For lyo screening, we replaced the salt with amino acid and also looked at low and high millimolar amino acids and with the sugar and surfactant. And then we wanted to see how does salt and amino acid combinations with a different ionic strength works for these formulations, and which led to our decision-making criteria based on protein concentrations, turbidity, particle diameter, polydispersity index, Kd, B22, viscosity, and osmolality. Now that we have described what our workflow is, this slide is intended to help you appreciate how we make decisions and the stoplight color coding we employ to rank order the data outputs. Here we illustrate the characterization assays we utilize to rapidly perform an initial formulation screening. As you can see, we have defined acceptable, must monitor, and not acceptable criteria for 11 different assays and attributes right from physical appearance to B22 and KD values. We began, as is commonly performed, with a simple pH and ionic strength screen to reconfirm solubility, colloidal, and biophysical stability. The Unchained, Unagi, Honeybun, and Stunner were utilized to buffer exchange IgM into 30 different conditions in a low volume, ultra-high throughput manner. Here I am showing different pHs with different salts and with sugar and surfactant formulations that were screened. The goal is not to tell you what we did, but how we did in a high throughput manner. These are the results from our liquid formulation screening. As you can see, indicated by the green heat map, specific combination of buffer and salt, chiefly low ionic strength at low pH, and higher concentrations of salt at neutral and high pH values. To the right, you would observe the additive benefit of combined impact of both sugar and surfactant further improved our measured attribute. Specifically, if you look at serial number 9 with pH 6 with high buffer, you see B22 and KD were negative. On the right table, you would see those turned positive with addition of sugar and surfactant. That shows that sugar and surfactant helps impart stability and have a better formulation. Knowing that salt is not good for the lyophilization process and the associated thermal properties, we utilized the Unchained ecosystem to screen the ideal concentration and ratios of amino acid to replace salts otherwise beneficial to liquid colloidal stability. We observe again in green that this strategy rapidly identifies potential formulations and concentration of amino acid across pH range. And we saw that with pH 4 to 8 with higher concentration of amino acid illustrating benefit at neutral pH, chiefly due to the proximity to this particular molecule isoelectric point at this pH. In sum, we were able to rapidly recommend 10 unique formulations to resume reformulation screening with only 30-hour delay. We recommended liquid formulations with pH 4 with no salt, pH 5 with low amino acid, sugar, and surfactant, pH 6, 7, 8 with high salt in the combination of sugar and surfactant. On the other side, lyophilization formulations were same for pH 4 and 5. With pH 6, 7, we went ahead with high amino acid content, and pH 8 with low amino acid content, which favored a suitable and a stabilized formulation. 5 key learnings are summarized here. We also initiated stability in parallel to control and support manufacturing window for pre-lyophilization. Recommendations in this case were made based on biophysical characterization for liquid and lyoformulation using Unchained ecosystem, and adding more salt and amino acid at neutral pHs stabilize the molecule and produce positive KD and B22 values. Also, adding sugar resulted in positive KD and B22 values for pH 6, 7, and 8 in high salt formulations. Lyoformulations were screened and identified by replacing the salt with amino acid.
The value of this workflow for our development activity is clear. We find clear benefit to screening and the assessment of stability. With respect to screening, we see the importance of exchange temperature and the method and process. We understand the importance of the ionic strength and the species utilized, and we observe a clear effect, a beneficial effect, of the sugar on the KD and B22. Finally, with respect to screening, this approach is incredibly resource sparing with respect to both material and time. Regarding stability, we observed that the neutral pH formulations with an adequate ionic strength exhibited the most optimal stability, and that lyoformulations perform better than liquid formulations. Ultimately, this translated to a more faster and efficient process that was material, time, and effort sparing, which led to a more rapid lead and backup selection for formulation recommendation. We've learned many things, but most critically, sugar imparts stability. We actually replicated that observation, which is known, but here we demonstrate that it resulted in positive and higher KD and B22 values as well. we observe a higher ionic strength and charge resulted in a higher Kd and B22 at neutral pHs closer to the pI. Further, replacement of salt with amino acid in lyoformulation specifically resulted in a similar data profile with respect to the biophysical characterization performed. And ultimately, this activity resulted in us being able to screen 30 formulations in 30 hours. In order to achieve 30 formulations in 30 hours, an efficient microfluidic, volume-sparing, and automated workflow was developed utilizing the Unchained ecosystem. On the left-hand side of your screen, you see a process. Specifically, you see the process beginning with buffer preparation or opening of a notebook, as is commonly performed, proceeding clockwise to the endpoint of this process of ultimately making a formulation recommendation. On the right side of your screen, you will see the old way or the old process for performing these activities on said 30 formulations, wherein typically one must supervise the entire process. In black, I show you time from that initial step of buffer preparation through the end of the analysis here, which amounts to 38 hours total of supervised workflow time. The material required for this old process is roughly 75 milligrams to perform this characterization activity. And then 8 hours for data analysis and compilation. Our new process, using the Unchained ecosystem, or load and go, as we like to refer to it, is 30 hours now, but it is fully unsupervised. The material requirements drop to 20 milligrams due to the low volume nature, and then our data compilation time decreases dramatically to only 2 hours. When we think about that information together with respect to a gain and benefit analysis, a very rough estimate is provided below on the right. We observe approximately a 21% improvement to time saved, an 8-hour workflow time saved plus 30 hours of unsupervised work to perform other tasks. Another way of saying this might be that 30 hours now to do the work, but it's 100% automated, meaning it is 21% faster to work in this fashion, and 100% of that time is now back to the analyst in the laboratory environment. Further, with respect to material, this workflow saves 73% of material, or in this case, specifically 55 milligrams. And finally, with respect to post-analysis time to actually making a decision or recommendation, we've saved 6 hours, or 75%. I will add that we have additional activity underway to further improve the inputs, the inline processes, as well as the output efficiencies for managing the data in this workflow as well. Thank you again for your time and attention today. We are happy to address any questions you may have.
Thank you, everyone, for that great presentation. We now have time for some questions. One of the first questions is, which of these products can be automated?
All right. Hi, everyone. This is Christopher Mensch. Maybe I'll go ahead and start. We have some perspective here. I'll also invite some perspective from the Unchained team. But I think it's important to first define what we mean by product. So in two sense, we can really answer this question, I think, appropriately. The first is in the sense of products. That development molecules, we believe they can be readily automated by this approach. And those include biologics, such as antibodies, therapeutic proteins, lipid nanoparticles, and formulation activities are a prime example of leveraging automation. The second part of that definition for us is technology as a product, and the generation of this data and knowledge, and how that fits into a workflow. For us, that includes the inputs, the active process, and the outputs, which we presented in the slide. all of these have the potential to benefit from automation approaches such as the one we developed, we believe.
Okay. And then from my perspective, taking kind of an instrument-first approach, so Stunner is ready to go for automation. It's consumable, the automation-compatible plate format that's going to work with pretty much every liquid handler out there. And then the instrument has a beautiful API that works really well with automation tools, so it's ready to go. Honeybun is actually really, really fast, so it doesn't necessarily need automation if the experiment is done in about 1 minute. So that's a product that can be loaded and run in less than 5 minutes to get you quick answers. And then Unagi is actually an automation solution itself. It's a robot that's designed to make buffer exchange simple, easy, quantitative, all those good things. So again, load the sample and then it's automation can take it from there.
Great. Thank you, Chris and Kevin. Another question that we have is, what is your perspective on integrating other automations on the input and output portions of the existing workflow that you use?
Yeah, I'll take that one. So on inputs, we would definitely have robotics for liquid handling, for formulation buffer preparation, dilutions, and plating, let's say in the Stunner plates or any consumables. Also allocating the stability samples into vials or for LC methods. As for outputs, we learned that we can do it in JUMP or other softwares which can actually manage the complex data generated through Stunner and develop data flows and analysis through different softwares.
Great. Thank you for answering that, Samir. Another question that we have is, what did you learn from your formulation screen that you've improved on in subsequent rounds of screening?
Sure, it's an excellent question. I'd say 4 key examples. The first being that the way in which we deploy USDS as a fit-for-scale part of our strategy, whether that be focused on material limitations early in development in that preclinical discovery space, right, pre-formulation, when you don't have the luxury of a lot of material and you're really in the world of microliters, right? And that's where I think some of the Unchained technologies, really shine, to be honest with you, being able to manage those microfluidics in those volumes. And then the second scale of the world of, as we like to say, hundreds of microliters, or in that milliliter, upper, hundreds of megs and gram territory. They all require different solutions and different workflows from our perspective, whether that be the application of an Unchained technology such as Unagi, or more traditional methods such as dialysis cassettes, spin columns, or even for larger volumes, things like TFF, right? The second thing I'd say we learned was how to manage the output activities, i.e. the data sets. As Samir mentioned, software solutions are really critically important, such as JUMP. We're also very mindful and exploring ideas for automating data flow into things like electronic laboratory notebooks, as well as the automation as much as we can in creating those presentations, right? There's more time left on the table here. It's the holistic workflow, not just this process. And so we really see the big picture on that aspect. On the other side of this, I just mentioned the output, but the input activities for us, we are using and leverage robotic liquid handling on the front end to perform dilutions for Stunner testing, for making formulation buffers, doing serial dilutions, moving that liquid around even before it enters the workflow that we spoke of. And then finally, what this has resulted in ultimately is the refinement of our design space for what our understanding is for how to achieve the goal, which is stability, and how to get to that decision sooner and be more material time and money sparing in the process.
Great. Thank you for answering that. Another question that has come in is, what is the difference between Unagi and Big Tuna?
This is one that I can take. So Unagi is our benchtop buffer exchange system. It's what was featured in the webinar today. And then Big Tuna is a more fully fleshed out automation solution for buffer exchange. And the difference is going to be volume and throughput. Unagi can run up to 8 samples, and it's sample holders are a little bit larger. And then big tuna usually runs in a plate-based format, so that's a 96 well or a 24 well plate-based format. So then you're dealing with more samples and then usually slightly smaller volumes per well. But then there's different ways you can combine the capabilities of those instruments to fit your need. So usually the best answer is to have a conversation with us, and we'll help you differentiate between those throughput and volume requirements to figure out what you need to do.
Great, thank you for clarifying that. Another question that's come in is, how exactly did you measure viscosity?
Okay, so viscosity in this case is measured on Honeybun. And what that is going to do is take a microfluidic chip and push the sample through that microfluidic channel using positive air pressure, and then with video, watch how fast that fluid flows. When you're trying to measure viscosity, you basically have three things. If you can know two of them, you'll figure out the third one that's just going to be viscosity. So in this case, we're applying known pressure, we're monitoring how fast it goes, and then viscosity can be calculated from there. The reason why we do this is because we're able to do it with a microfluidic chip that's relatively inexpensive. It means you can use it once and not have to worry about it clogging or breaking, which happens a lot of the time when you're dealing with other ways of doing viscosity measurements. So it's a way of getting really fast, inexpensive, and easy viscosity measurements.
Great.
Yeah, and I'll add to that we have also compared this with conventional methods such as rolling ball and Tron power, and we got data values which are within 5% difference. Even at this concentration, we do not see much difference between the conventional versus Honeybun method.
Great, thank you both of you for those answers. Another question that we have is, what is your perspective on either existing or non-existing technologies that could further enhance this workflow?
Sure, I'll field that one. Again, this is Chris. So if we just focus, I think, on the active process here for this answer, we can expand it. But I think you could package a more complex workflow potentially into systems that some of us probably on the call today are familiar using. I know myself and others I see on the call, TCANs, Hamiltons, or even something like the Unchained Big Kahuna, right? That's another opportunity. On USDS steps specifically, if we drill down to that level, for our process, we're exploring the opportunity. We have a big tuna, right? And as Kevin said, 96 samples, 100 microliter volume, it's different. It's a different use case, right? And so it's all about trying to really appreciate and know the problem you're trying to solve, and then apply the appropriate technology to achieve that goal to be successful, right? And I think that definitely represents, an opportunity for significantly increasing our throughput. On that last step of the process, I'll be honest, we clearly recognize the opportunity to integrate further technologies, inclusive of another one that we have, which is the Uncle from Unchained, which is an alternative to Stunner, right, to determine TM values by fluorescence. And we have added thoughts here. More, we didn't discuss it today, but there are a number of already plate-based or automated formats, maybe they're not microfluidic, but other technologies from a biophysical characterization perspective and others, LC methods that we've integrated into the workflow that work quite nicely.
Great. Thank you for that answer. Another question that's come in is, can these products be used in GMP environments?
Yeah, I can answer that one. So Stunner is ready to go. It has 21 CFR Part 11 software tools. It has standards that you need to confirm performance. It even has standards that you can compare against the U.S. Pharmacopoeia and European Pharmacopoeia requirements for that kind of instrument. So it's set up for GMP environments. And then Honeybun and Unagi, they have capabilities that make it a lot easier to integrate into GMP environments. So parts of the software that are ready to add 21 CFR Part 11 capabilities, they're kind of more set up for a research environment, but everything has some flavor that gets you into a GMP environment.
Okay, great, thank you. Another question we have is it possible to analyze composites containing protein?
So that one's not completely clear what that might be by composites. If it's nanoparticles, the answer is going to be yes. If it's going to be basically anything in solution, usually we can figure that out and get some good results on something like Stunner. So that's the kind of thing where we should definitely have a further conversation and explore the details there.
Okay. We have one more question. Can you compare formulations of biologics that are quite different in composition using Honeybun and using a common standard curve? Or would each formulation need its own standard?
Okay. So on Honeybun, you actually don't need to run standards. So on each consumable, we know the dimensions of it. It's actually coded on each consumable using a QR code. So if you know the dimensions and you can measure speed and you can measure pressure, that's everything you need to get viscosity without any sort of standard. So each formulation can be run on its own, or if you want to, you can run, say a protein sample and a buffer blank next to each other to see the impact of proteins. Pretty much designed to be as fast and user-friendly as possible.
Great. Thank you for that answer. I think we're going to wrap up there. If we didn't get to your question, they will be passed along to the speakers who can follow up by email. Thank you again, everyone, for your presentation, and thank you, participants, for being a great audience. Please be sure to check C&EN or C&EN Online for the replay of this webinar and information on the next edition of C&EN webinars. Thank you, On24, for technology and production services, and thank you, Unchained Labs, for the sponsorship that made this interactive webcast possible. For C&EN webinars, I'm Ann Thayer. Hope you all have a good day.
Thank you much.